Assalamu alaikum. We have started about the chapter of central forces, in which we have discussed about that all the forces act towards the center. And for classical mechanics, as we are dealing with the systems, so that is very much important that we should understand these central forces. This chapter is central force, and it is from classical mechanics for BS 5th, and the course code is PHY 509. Now moving to the central forces, in which we will discuss that all the mass is concentrated on a specific point. If there are number of bodies, we can consider them as one body. So for this we will work now and take a two body system and find the relation according to the central force. Now we are going to start the conversion of two body problem into one body problem. Here you can see a graph or a picture that represents the three coordinates x, y, z and a central point origin O. There are two position vectors r1 and r2. The position vector towards the mass m1 is r1, and the position vector towards the point or mass m2 is r2. You know that if there are two masses in a system, they exert a equal and opposite force on one another. So it means that M2 is exerting a force on mass M1, and its force will be F12, and you can see that M1 will provide a force on M2, that will be F21. The spacing or the distance between the 2 points M1 and M2 is R is equal to R1 minus R2, that is the difference between the two position vectors. Now moving on to the pictorial representation of the system, we can say that consider an isolated system consisting of two particles with mass m1 and m2 having position vectors r1 and r2 with respect to origin O interacting under a central force. It means that the force exerting from m2 to m1 is F12, and the force exerting from m1 to m2 is F21. That I have told you in the picture representation as well. As we know that F12, which is equal but opposite to the force exerted on the M2 by M1, which is F21, thus the equation of motion of two particles will be written as F21 is equal to M1 R1 double dot is equal to minus F of R AR, that is equation 1. And here you can see that R1 double dot is the acceleration representation, and that equation is like the force is equal to ma. Here acceleration is represented by r double dot, so we have written for the position vector r1 acceleration r1 double dot, and that is the central force. We know that central force is f of r unit vector ar, and you know that two forces are equal and opposite, so we have substituted a minus sign with the equation 1 minus f of r ar unit vector. Now F12 is equal to M2 R2 double dot is equal to F of R AR unit vector, that is equation 2. Equation 1 and equation 2 are coupled together by the equation given as R is equal to R1 minus R2, giving that equation number 3. The solution of such coupled equation becomes relatively easier if we introduce a coordinate capital R for the central mass of the system. As we know, you know that all if there is a number of particles in a system, their mass is concentrated on some specific point, and that is represented by a center of mass capital R or center coordinate capital R. So we will consider here the position vector capital R, which is due to the mass concentrated by the particles. Here are two particles, so both particles mass is concentrated on some specific point capital R. Here capital R is equal to summation I mi Ri divided by summation I mi, and capital R is equal to m1 R1 plus m2 R2 divided by m1 plus m2. Here you can see that in the previous picture we have two masses and two position vectors, so you know that summation will represent for these 2 points and their respective position vectors. Cross multiplying m1 plus m2 on with the capital R, we get m1 plus m2 capital R is equal to m1 R1 plus m2 R2. Giving that equation number 4. Now multiplying equation 3 previous by m2 and adding with the equation 4. So we get m2r is equal to m2r1 minus m2r2. Giving that equation number 5. So now adding these two equations, we have m1 plus m2 into capital R is equal to m1 r1 plus m2 r2. And second equation m2r is equal to m2r1 minus m2r. Here you can see that the plus and minus sign of m2 r2 are cancelling, so we cancel that terms. Remaining terms are written as m1 plus m2 into capital R plus m2 small r is equal to m1 plus m2 into r1. Now cross multiplying m1 plus m2 on the left hand side, we get as r1 is equal to capital R into m1 plus m2 plus m2 over r, m2r over m1 plus m2, and then taking the LCM on both sides of m1 plus m2, we get r plus m2 over m1 plus m2 into r, that is equation 6. I hope till here you have understood. I will give you some time to write down that equation with me. You know that r is equal to r1 minus r2. From here we can get the equation for r1. r1 is equal to r plus r2. Substitute that value in the previous equation, we get r plus r2 is equal to capital R plus m2 over m1 plus m2 into r. r2 is equal to capital R plus m2 over m1 plus m2 into r minus r. Taking the r from the left hand side on the right hand side with the negative sign, so the remaining term is r2 is equal to r plus m2 over m1 plus m2 into r minus r. From here r2 is equal to r plus taking the r common, we get m2 over m1 plus m2 minus 1 in the bracket, and then taking the terms in the bracket, r2 is equal to r plus, and inside the bracket we have m1 plus m2 in the LCM. So in above we have m2 minus m1 minus m2, cancelling the two m2's with the plus and minus sign, we get r2 is equal to r plus minus m1 over m1 plus m2 into r. So from here we get r2 is equal to r capital R plus minus m2 over m1 plus m2 into small r. Then r2 is equal to r minus m2 over m1 over m1 plus m2. The m2 was cancelled on the previous equation, so we have left with the m1, that is the equation number 7. Now multiplying the equation 6 with m1 and taking the second derivative, so we have m1 r1 double dot is equal to m1 r double dot plus m1 plus m2 over m1 plus m2 into r double dot, giving that equation number 8. Now multiplying the equation 7 with m2 and taking the second derivative, m2 r2 double dot is equal to m2 into capital R, capital R double dot minus m1 m2 over m1 plus m2 into R double dot, giving that equation number 9. Now comparing equation 1 and 8, we get minus f of r a r is equal to m1 r capital R double dot plus m1 m2 over m1 plus m2 into R double dot, and that is the equation number 10. Now comparing equation 1 and equation 11, f of r a r unit vector is equal to m2 R double dot minus m1 m2 over m1 plus m2 R double dot. Adding these two equations, we get 0 is equal to m1 plus m2 R double dot plus 0, as plus and minus terms are cancelled. So we are left with the equation R double dot is equal to 0, that is the acceleration. It means that the acceleration is 0 in the equation 12, and again taking the derivative, if we take the derivative, we see that the velocity component in the differential form capital R dot is equal to 0. It means if acceleration is 0, the velocity is 0. This means that center of mass moves with a constant velocity. It means that there is no change in the acceleration or velocity. Now integrating the equation 12 twice and applying the initial conditions capital R can be worked out. Here we are not doing this, but we can find out this value. To find out the equation of motion in terms of small r, we shall make use of equation 1 and 2. We have r1 double dot is equal to minus f of rm into ar unit vector over m1, that is equation A. Similarly, r2 double dot is equal to f of r ar unit vector over m2, that is equation B. Subtracting the two equations B from A is equal to f of r1 double dot minus r2 double dot is equal to minus f of r into ar unit vector over m1 minus f of r ar unit vector over m2, and then after integrating we get sorry, not integrating but taking the common, r1 double dot minus r2 double dot is equal to f of r ar unit vector into 1 minus 1 over m1 minus 1 over m1 minus 1 over m2. Taking the minus on common, we have r1 double dot minus r2 double dot is equal to minus f of r ar unit vector into 1 over m plus 1 over m2. Also we know that r1 minus r2 is equal to r. Similarly, then r1 double dot minus r2 double dot will also be equal to r. So substituting that value, we get r double dot is equal to minus f of r ar unit vector into 1 over m1 plus m2, 1 over m2. R double dot is equal to minus f of r ar unit vector into m2 plus m1 over m1 plus m2. Now r2 double dot is equal to minus f of r ar unit vector into m1 plus m2 over m1 m2. Then m1 m2 over m1 plus m2 r double dot is equal to minus f of r ar unit vector. We have cross multiplied the equation, that is equation C. Then minus f of r ar unit vector is equal to m1 m2 over m1 plus m2 r double dot, that is equation D. Now taking that mu is equal to m1 or m2 over m1 plus m2, that is called the reduced mass, that the many or the two body problem is converted into reduced mass. Then F is equal to m is, then similarly according to that equation, minus f of r ar unit vector is equal to mu r double dot. Here mu is the reduced mass, that is the similar equation for the as for F is equal to ma. Equation 14 is identical to equation of motion of the particle of mass mu acted upon by a force minus f of r unit vector. Thus the two body problems has been transformed into one body problem by which r can be determined. Once we know the value of a capital R and R, we can work out for R1 and R2 by using the equation relation 6 and 7, and also mu is known as reduced mass.
Start looking at what is called two-body problem. Okay, here you have two particles of masses m1 and m2 which are interacting with each other and there are no external forces present. Okay, so that's the situation. So you have a particle of mass m1, another particle of mass m2. Okay, and let's say this guy is located at r1 and this particle is located at R2 with respect to some origin, which let's say it's here, which means this is R1 and this is R2. Okay, and these two particles are interacting with each other, and let's say the potential energy due to that interaction is U of R1 R2. Okay, so the interaction is given by the potential energy R1 R2. It's a function of R1 and R2, and there are no external forces on this system. So this is what is a two-body problem. So you have two particles, two bodies, and they are interacting in a certain way. So here I have made an assumption that the potential energy only depends on where the particles are. Okay, that's the assumption I have made. But now I want to further assume, which is very reasonable, further assumptions. Okay. So I assume that the force is such that the potential energy does not change if you take the entire system and move it to somewhere else. Okay, meaning it cares only about what is the difference between R2 and R1. Okay, so if I translate this entire thing by some amount, the potential energy does not change. So I am saying that U of R1 R2, okay, is same as U of R. Let me put the first one here, and this does not matter. So here what I'm saying is it cares only about the vector which is separating them. Okay, the difference vector R2 minus R1. Okay, that's nice, and this of course is not unreasonable. This is a very reasonable assumption, because that's how most of the things will behave. If, for example, you think of two particles which are interacting gravitationally, if you take the entire system and shift it to another place, millions of kilometers away or billions of kilometers away, the potential energy between those two will not change. Okay. Now, not only that, we want to further assume that U of R1 R2 is only dependent on the distance between these two particles. Okay, so this is clearly different from this. Here it still depended on the direction in which R2 minus R1 will point, right? So here let's say this is R2, this is R1, so this vector, this is R2 minus R1. So when I write here this way, it means that the potential energy cares about in which direction this vector is pointing. So if you rotate this, for example, this entire setup, then the R2 minus R1 will be pointing in some other direction, and it says that, okay, it may depend on it. And here I am going to be more specific and saying that even if you rotate this so that the direction of R2 minus R1 changes, it still does not change if the separation distance is fixed. Okay, that is what is meant by this expression, which is also not unreasonable. This is a very reasonable choice, because you know that space is homogeneous and isotropic. So if my system is not being affected by any other external agents, then space will be homogeneous and isotropic, and translating as a whole the entire thing, or even rotating the entire setup, should not change how the system is going to behave, which means that the potential energies should be given by such restricted form. Okay, let's see. Yeah. Now, if this is the case, then we say that the force is central. Okay, central force, which means just that your potential energy depends only on the separation between the two particles of your system. That's a central force field. Okay, now let's ask, I mean, we would like to solve this system, and this system is solvable. We will see that we'll be able to find the full solution to this. But at the moment, the goal is to figure out as much we can about the system without specifying anything about the potential other than what we have already said. Okay, so I do not want to assume any special form for the potential, that it falls off this way or that way, and I want to see how much I can say about such a system just based on the fact that this is a central force system. Okay, so one thing is clear, that this is a 6-dimensional system. This has a 6 degrees of freedom, which is obvious. Each particle has 3 degrees of freedom. So the system is a system of 6 degrees of freedom. And let me try to create a separation. Yes. Okay. Okay, fine. So what's the Lagrangian of this system? It's easy to write. It's just the kinetic energy minus the potential energy, and we have already written down the form of potential energy. So your L, the Lagrangian, is half m1 r1 dot square plus half m2 r2 dot square minus the potential energy, which is r2 minus r1, the modulus of it. Okay, it cares only about the length. Now we ask whether these are the best coordinates to describe the system. Now our experience with several different systems before may immediately tell us that these are not the best coordinates. It would be wise to use r2 minus r1, the modulus of it, as one of the coordinates, and the other coordinate which will be good to use will be the center of mass coordinate. Okay, we have come across this thing several times, so I will not go further into this and just write down the transformation. Okay, so what we want to do is we want to do a transformation of coordinates from r1, which is, I will call x1, y1 and z1, and r2, which is x2, y2 and z2, and from this I want to go to r, capital R, by which I denote the center of mass, m1 r1 plus m2 r2 over the total mass of this system, which is m1 plus m2, and small r, which is r2 minus r1. So I go from these 6, 1, 2, 3, 4, 5, 6 to these 6, because R is of 3 vectors, so it has 3 components, and small r is also 3 vector, it has 3 components. So I've gone from 6 to 6, and let's see why this will be very useful. But before we do that, let's invert this and write down R1 and R2 in terms of capital R and small r. Okay, so please do this exercise, and VERT, correct. So please check that what I'm writing is correct. R1 you can write as the center of mass, location of the center of mass, minus m2 over m1 plus m2, and this small vector r, which is the separation vector, and then your R2 is this plus m1 over m1 plus m2 times r. Okay, that's nice, and this will be very useful, because when I try to find out what the kinetic energy is, which is here, this in this place, and when I substitute these R1 and R2 in there, I find a very nice result, which is kind of expected. So please do the following exercise and check. Okay, I had a plan of using green when I'm giving exercises. Okay, so please check that the kinetic energy T becomes half m kinetic energy, which is half m1 r1 dot square plus half m2 r2 dot square, becomes half m1 plus m2 r dot square, which is the coordinate of the center of mass, so the velocity of center of mass square, plus half m1 m2 over m1 plus m2 r dot square. Okay, let me check the dimensions. So I have 2 powers of mass here, 1 power of mass below, so it makes 1 power, which is consistent with this one, so it looks fine. Okay, good. Now let me define by capital M, m1 plus m2, the total mass, and I also introduce mu to be the following. Okay, so that's the definition of mu, and you can see that this piece here, m1 m2 over m1 plus m2, is just mu. Okay, and mu is called the reduced mass. So with this, what is our Lagrangian now? Our Lagrangian looks like the following. So my Lagrangian is now half m r dot square. Then you have the reduced mass term, which is half mu r dot square, and then we had the potential term, which is u of r. Okay, where I have introduced new notation, which is r2 minus r1. So this vector, this r without any vector symbol, is this quantity. Okay, that is good, and it's nice because you see the coordinate capital R, the center of mass coordinate, that is a cyclic coordinate, which is what you expected. Okay, this is nice because now I can immediately solve the equation of motion for capital R, and I know what I will get. I mean, you can do it, but that's what you're going to get. The equation of motion for R is R dot is equal to constant, which just says that the center of mass moves with a constant velocity. That is what is expected. And then we can drop it from the Lagrangian, because the equations of motion of other coordinate R is not going to be affected by what is happening to capital R. So I can take my Lagrangian to be half mu R dot square minus U of R. Okay. Now you see, this is very nice because this looks like, I mean, not like, it is exactly of the same form as of a particle of mass mu, which is moving in a potential field which is given by U of R. Okay, central potential field. So this Lagrangian is same as the Lagrangian of a particle of mass mu moving in a force field U of R. So you understand what is happening? You started with a system which had two particles, but with a good choice of coordinates, the system appears to be equivalent to another system, which is a very simple system where you have a particle of mass mu which is moving in a center force field which is given by U of R. Okay, that is what it looks like. So if you can solve this system, this new one to which we have reduced our original system, if we can solve it, I can invert back. So let's say I solve for small r and I have capital R. From that I can construct my R1 and R2 and I will know about my original problem. Right? So that is what will provide us the full solution to this problem. Okay, so we will now proceed from here and ask whether I can further make a better choice of coordinates. Okay, I went from R1 and R2 to capital R and small r, which was center of mass and the separation between the two particles, which immediately gave me a cyclic coordinate, and I could get rid of that coordinate from my Lagrangian. I would like to ask whether there is still something I can do about the coordinates. Can I choose a nice coordinate? And you can see why I might be thinking about this, because you have here only the magnitude of that vector r. Okay, so I can do more. So this is what we will look at next.
तो फिर चलिए आज के इस वीडियो में हम केपलर्स लॉज ऑफ प्लैनेटरी मोशन पे बात करेंगे। देखिए, जो प्लैनेट्स है ये सन के चारों तरफ रिवॉल्व करता है, तो उसी तरह के मोशन को कहा जाता है प्लैनेटरी मोशन। केपलर ने 3 लॉज दिए थे रिलेटेड टू प्लैनेटरी मोशन। प्लैनेट जो सन के चारों तरफ जिस तरह से रिवॉल्व कर रहा है, इसके पीछे के 3 लॉज उन्होंने दिया था। पहले लॉ में केपलर कहते हैं द ऑर्बिट ऑफ अ प्लैनेट, प्लैनेट जिस पाथ में सन के चारों तरफ घूम रहा है उस पाथ को ऑर्बिट कहा जाता है। द ऑर्बिट ऑफ अ प्लैनेट इज एन एलिप्स विद द सन एट वन ऑफ द फोकाई। चलिए, सबसे पहला सवाल तो ये होगा कि आखिर ये एलिप्स है क्या। चलिए देखते हैं एलिप्स है क्या, और ये फोकाई का मतलब क्या है। एक्चुअली ये फोकस का प्लूरल फॉर्म है फोकाई। तो चलिए, फोकस एक एलिप्स का ये क्या होता है ये भी हम देखेंगे। सबसे पहले चलिए देखते हैं एलिप्स क्या होता है। तो मान ले एक सर्कल है। अब इस सर्कल को अगर हम चपटा कर देते हैं तो यही बन जाता है एलिप्स, इसी को हम एलिप्स कहते हैं। अब चलिए इसे सर्कल के साथ कंपेयर करके देख लेते हैं। लेट्स से ये एक सर्कल है और ये रहा उसका सेंटर। तो सर्कल एक ऐसा शेप है जहां पर कि उसका हर एक पॉइंट, चाहे पॉइंट यहां पर हो, चाहे पॉइंट यहां पर हो या फिर यहां पर हो, इसका हर एक पॉइंट सेंटर से उनका जो डिस्टेंस होगा, ये वाला डिस्टेंस, ये डिस्टेंस सेम होता है और इस डिस्टेंस को हम क्या कहते हैं? रेडियस कहते हैं। इसे चलिए r से डिनोट कर लेते हैं और इस पॉइंट का भी डिस्टेंस सेंटर से उतना ही रहेगा r, सेम डिस्टेंस, चाहे पॉइंट कहीं भी हो, सर्कल पे पॉइंट कहीं भी हो, सेंटर से उसका डिस्टेंस सेम रहेगा। ये सर्कल का डेफिनेशन है। अब जैसे सर्कल का सेंटर होता है, एलिप्स के साथ भी कुछ ऐसा ही चीज़ एसोसिएटेड होता है, उसे कहा जाता है एलिप्स का फोकस। एलिप्स का एक फोकस नहीं होता है बल्कि दो फोकाई होता है। सर्कल का एक सेंटर होता है और एलिप्स का दो फोकाई होता है। यहाँ पर ये एक फोकस, ये दूसरा फोकस। अब देखिए एलिप्स डिफाइंड कैसे होता है। इस एलिप्स का ये एक फोकस और ये एक फोकस। इस एलिप्स में किसी भी एक पॉइंट को कंसीडर कर ले, लेट्स से ये वाला वो पॉइंट है, तो एक फोकस से इसका जो डिस्टेंस है और दूसरे फोकस से इसी पॉइंट का जो डिस्टेंस है, इन डिस्टेंसेस को चलिए नाम दे देते हैं। ये सीधा नहीं हुआ लाइन, ये स्ट्रेट लाइन होगा। दो डिस्टेंसेस को नाम दे देते हैं L1 और ये L2। तो ये जो L1 और L2 का सम होगा, ये सम कांस्टेंट होगा। कहने का मतलब ये है पॉइंट कहीं भी हो, पॉइंट यहाँ पर अगर हो तो एक फोकस से इस पॉइंट का डिस्टेंस और दूसरे फोकस से इस पॉइंट का डिस्टेंस, इन दोनों का सम जो है ये कांस्टेंट होगा। लेट्स से ये L3 है और ये लेंथ L4 है, तो L3 प्लस L4 L1 प्लस L2 के बराबर होगा। L3 प्लस L4 इज इक्वल टू L1 प्लस L2। चाहे पॉइंट कहीं भी हो, यहाँ पॉइंट कंसीडर करें और एक फोकस से यहाँ इसे जोड़ दे, दूसरे फोकस से इसे जोड़ दे। ये वाला लेंथ जो है, चलिए इसे नाम दे देते हैं L5 और ये वाला जो लेंथ है ये है L6, तो इसी के बराबर होगा L5 प्लस L6। तो इस तरह से एलिप्स को डिफाइन किया जाता है कि ऐसा एक शेप जिसके हर एक पॉइंट, जिस पे हर एक पॉइंट का दोनों फोकाई से जो डिस्टेंसेस है उनका सम ये फिक्स्ड हो, ये कांस्टेंट हो। तो ये तो हो गया एलिप्स का डेफिनेशन। अब देखते हैं ये जो फर्स्ट लॉ है केपलर का, फर्स्ट लॉ ऑफ प्लैनेटरी मोशन, ये क्या कह रहा है कि प्लैनेट्स का जो ऑर्बिट है, जिस ऑर्बिट में, जिस पाथ में ये सन के चारों तरफ घूम रहा, ये जो ऑर्बिट है ये एक एलिप्स होता है। वैसे अब तक हम जो भी अपने किताबों में देखते हैं उससे हम एक अंदाज़ा बनाते हैं और हमें लगता है कि सन के चारों तरफ प्लैनेट्स जो है सर्कुलर पाथ में रिवॉल्व करता है। वैसे सर्कुलर पाथ में रिवॉल्व करना बहुत 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 किस्मत वाली बात है, क्योंकि सर्कल जो है एलिप्स का एक बहुत ही स्पेशल फॉर्म है, ना इधर से चपटा ना उधर से चपटा, बिल्कुल गोल। तो ये बहुत किस्मत की बात है, ऐसा नॉर्मली नहीं होता है। तो प्लैनेट्स जो है उसका जो पाथ होता है, जो ऑर्बिट होता है, वो नॉर्मली एलिप्स होता है। तो ये एलिप्टिकल पाथ में घूमता है और सन इसके एक फोकस में होता है, वन ऑफ द फोकाई। दो फोकाई में से एक फोकस में सन सिचुएटेड होता है। लेट्स से ये अर्थ का ऑर्बिट है, ये अर्थ है और ये अर्थ का ऑर्बिट है। तो अब ये जो एलिप्टिकल पाथ में घूम रहा है, ये जो एलिप्स है, इस एलिप्स के किसी एक फोकस में रहेगा सन, सिचुएटेड होगा सन। तो लेट्स से सन यहाँ पर सिचुएटेड है। तो फर्स्ट लॉ, केपलर्स फर्स्ट लॉ ऑफ प्लैनेटरी मोशन, ये हमें यही चीज़ बताता है कि प्लैनेट्स का जो ऑर्बिट है ये एलिप्टिकल होगा और सन उस एलिप्स के एक फोकस में सिचुएटेड होगा। अब चलिए दूसरा लॉ जो है इसे भी देख लेते हैं। द लाइन जॉइनिंग द प्लैनेट एंड द सन स्वीप इक्वल एरियाज इन इक्वल इंटरवल ऑफ टाइम। चलिए इसे समझते हैं कि इसका मतलब क्या होगा। सबसे पहले तो देखिए यहाँ पर इक्वल इंटरवल ऑफ टाइम कहा गया है। चलिए देख लेते हैं इस पूरे चीज़ का मतलब क्या है। मान ले कि अर्थ अभी यहाँ पर है, वैसे तो अर्थ तो ये रिवॉल्व करेगा इस पाथ में, इस एलिप्टिकल पाथ में। ये एक बार सन का पूरा चक्कर लगाने में कितना समय लेता है? नियरली 365 डेज, 365 डेज एंड नियरली 6 आवर्स। तो इतना समय इसे पूरा चक्कर काटने में लग जाता है। चलिए हम कंसिडर कर लेते हैं 1 महीना, 30 डेज। चलिए 30 डेज बाद अर्थ डेफिनेटली यहाँ कुछ आगे होगा। यहाँ पर मैं आपको बता दूँ, ये ऑब्वियसली स्केल में नहीं है। अर्थ और सन का साइज लगभग बराबर दिख रहा है आपको, ये स्केल में नहीं है। सो 30 डेज बाद अर्थ लेट्स से कि यहाँ तक पहुँच गया, यहाँ घूमते यहाँ से यहाँ तक पहुँचा 30 डेज में, 30 डेज। तो ये जो कह रहा, द लाइन ज्वाइनिंग द प्लैनेट एंड द सन स्वीप इक्वल एरियाज इन इक्वल इंटरवल ऑफ टाइम। सबसे पहले तो ये देखें, लाइन ज्वाइनिंग द प्लैनेट एंड द सन, मतलब ये लाइन हमने ज्वाइन कर दिया दोनों के सेंटर को। स्वीप इक्वल एरिया, मतलब ये कुछ एरिया स्वीप करेगा। 30 डेज में अर्थ जो यहां से यहां पहुंच गया, तो ये जो लाइन है, लाइन ज्वाइनिंग सन एंड अर्थ, ये जो एरिया स्वीप कर रहा है, ये जो एरिया होगा, ये वाला एरिया होगा। ये 30 डेज में ये जो लाइन है, ये इतना एरिया स्वीप कर रहा है। अब ये कहा गया कि ये जो एरिया स्वीप करेगा ये इक्वल होगा इन इक्वल इंटरवल ऑफ टाइम। इसका मतलब 30 डेज बाद और फिर से 30 डेज बाद ये अर्थ जो है, लेट्स से ये अर्थ यहाँ पर आ गया घूमते 30 मोर डेज। सो 30 डेज मोर, फिर से 30 डेज बाद ये यहाँ पर आया। अब ये जो लाइन होगा अर्थ और सन के बीच का जो लाइन होगा, ये अब इन 30 डेज में, यहाँ से लेके यहाँ तक इन 30 डेज में कितना एरिया स्वीप करेगा, वो एरिया होगा ये वाला। Let us say this area is A1 and this area is A2। तो देखिए इंटरवल ऑफ टाइम देखिए इक्वल है, 30 डेज एंड 30 डेज। तो इक्वल इंटरवल ऑफ टाइम में ये जो एरिया स्वीप करेगा वो एरिया बिल्कुल बराबर होगा। दैट मीन A1 शुड बी इक्वल टू A2। यही है केपलर का सेकेंड लॉ ऑफ प्लैनेटरी मोशन। अब चलिए थर्ड लॉ की तरफ बढ़ते हैं, उससे पहले मैं इस चीज को मिटा देता हूं। तो थर्ड लॉ जो है ये कहता है द क्यूब ऑफ द मीन डिस्टेंस ऑफ अ प्लैनेट फ्रॉम द सन। वैसे देखा जाए तो अगर एलिप्टिकल पाथ में ये घूमेगा, सन अगर वन ऑफ द फोकाई में होगा, तो फिर ये डिस्टेंस जो होगा सन के साथ इस प्लैनेट का, यहाँ पर एग्जांपल के तौर पे हमने अर्थ माना था, तो सन और अर्थ के बीच का जो डिस्टेंस है ये डिस्टेंस सेम नहीं होगा। देखिए ये जब घूम फिर के यहाँ पर आएगा घूमते हुए तो ये डिस्टेंस कम हो जाएगा, फिर जब यहाँ पर आएगा फिर डिस्टेंस बढ़ते जाएगा। सो ऐसे में ये जो डिस्टेंस है ये डिस्टेंस सेम नहीं है। तो मीन डिस्टेंस का मतलब है एवरेज डिस्टेंस। यहाँ से सन से अर्थ का जो डिस्टेंस है उसका जो एवरेज होगा पूरे 365 डेज में एक बार पूरा चक्कर लगाने में, जो इसका एवरेज डिस्टेंस होगा, उस एवरेज डिस्टेंस की बात किया जा रहा है। लेट अस से दैट एवरेज डिस्टेंस इज आर। चलिए हम मान लेते हैं ये एवरेज डिस्टेंस आर से हम डिनोट करेंगे। सो द क्यूब ऑफ द मीन डिस्टेंस ऑफ अ प्लैनेट फ्रॉम द सन इज प्रोपोर्शनल टू द स्क्वायर ऑफ इट्स ऑर्बिटल पीरियड टी। अब यह ऑर्बिटल पीरियड क्या होता है? एक बार पूरा चक्कर लगाने में, इसके पूरे ऑर्बिट में एक बार पूरा चक्कर लगाने में जितना समय लगता है, दैट इज नियरली 365 डेज फॉर अर्थ। अर्थ के लिए ये लगभग 365 डेज होता है, 365 डेज एंड नियरली 6 आवर्स। तो ये जो ऑर्बिटल पीरियड है, दैट मीन एक बार चक्कर लगाने में जो समय लगा, इस ऑर्बिटल पीरियड को हम कैपिटल टी से डिनोट कर रहे हैं। अब इस स्टेटमेंट का मतलब ये होगा कि मीन डिस्टेंस, जिसे कि हम स्मॉल आर से डिनोट कर रहे थे, सो मीन डिस्टेंस का क्यूब, मीन डिस्टेंस का क्यूब ये प्रोपोर्शनल होगा इसका जो टाइम पीरियड है, इस प्लैनेट का जो टाइम पीरियड है उस टाइम पीरियड के स्क्वायर पे। तो ये हो गया केपलर का थर्ड लॉ ऑफ प्लैनेटरी मोशन। वैसे केपलर के इन 3 लॉज में ये क्लियर नहीं है कि ऐसा कौन सा एजेंट है जिसके कारण कि अर्थ सन के चारों तरफ इस तरह से रिवॉल्व करता है, या कोई भी प्लैनेट अपने स्टार के चारों तरफ क्यों रिवॉल्व करता है। उसका आंसर न्यूटन के यूनिवर्सल लॉ ऑफ ग्रेविटेशन से मिलता है, जहां पर ये क्लियर होता है कि दो मासेस के बीच, लेट अस से दैट इज, इसका मास कैपिटल एम है, इसका मास स्मॉल लेटर एम है, दो मासेस के बीच एक फोर्स एक्ट करता है जिसे ग्रेविटेशनल फोर्स कहा जाता है, और वो फोर्स एक दूसरे के तरफ होता है। यहां पर ये जो फोर्स है सन पे लगा हुआ फोर्स अर्थ के तरफ होगा, अर्थ पे लगा हुआ फोर्स जो है ये सन के तरफ होगा, और ये जो फोर्स है फ्रॉम यूनिवर्सल लॉ ऑफ ग्रेविटेशन हम ये पाते हैं दिस फोर्स इज इक्वल टू अ कांस्टेंट, जिसे कि यूनिवर्सल ग्रेविटेशनल कांस्टेंट कहा जाता है, इनटू मास ऑफ द फर्स्ट बॉडी इनटू मास ऑफ द सेकंड बॉडी डिवाइडेड बाय इन दोनों के बीच का जो डिस्टेंस है, यहाँ से लेके यहाँ तक का जो डिस्टेंस है, इस डिस्टेंस का स्क्वायर। तो ये है यूनिवर्सल लॉ ऑफ ग्रेविटेशन। अब ये जो यूनिवर्सल लॉ ऑफ ग्रेविटेशन है, ऐसा कहा जाता है न्यूटन को केपलर के थर्ड लॉ से काफ़ी मदद मिला था। थर्ड लॉ से ये न्यूटन पता लगाए थे, ऐसा कहा जाता है, ये पता लगाए थे कि हाउ दिस फोर्स, दिस ग्रेविटेशनल फोर्स इज इनवर्सली प्रोपोर्शनल टू द स्क्वायर ऑफ द डिस्टेंस। वैसे इस पे हम आज के इस वीडियो पे बात नहीं करेंगे, वो हम अगले वीडियो में देखेंगे कि न्यूटन कैसे पता लगाए होंगे कि हाउ दिस फोर्स इज इनवर्सली प्रोपोर्शनल टू द स्क्वायर ऑफ द डिस्टेंस। तो उस वीडियो का लिंक आपको यहाँ पर स्क्रीन पे मिल जाएगा, यहाँ क्लिक करके आप उस वीडियो को देख सकते हैं। तो आई होप कि यह वीडियो आपके लिए हेल्पफुल रहा होगा। अब जाते जाते मैं आपको बता दूं कि इस पूरे चैप्टर स्टैंडर्ड 9th के लिए ग्रेविटेशन चैप्टर, इसके सारे वीडियोस का जो प्लेलिस्ट है उसका लिंक आपको नीचे डिस्क्रिप्शन में मिलेगा। तो उम्मीद है कि अगले वीडियो में फिर मुलाकात होगी। तो मिलेंगे आपसे अगले वीडियो में, तब तक के लिए खुश रहें। गुड बाय।
Two body problem into reduced mass or the one body problem. Now there are some examples or the laws that are called the Kepler's planetary law. He dealt with the law that the planets are not in a circular motion but in an elliptical path. So from there we are going to work out for Kepler's planetary law. First, Kepler's first planetary law. They find the equation of orbit when the law of force is given. Then the motion of planet around the sun is not helpful for a motion under the central force. Basically, it is a two body problem. We can convert into the one body problem. As the distance r of the sun to the planet and replacing the mass by reduced mass, mu is equal to capital small m over m1 plus small m. As smaller mass m of the planet is very small than the mass of the sun, capital M, then we can neglect the terms capital M over capital M. Cancelling m with m, we get mu is nearly equal to small m. The law of force in this case will be square. Substituting the value for g, k is equal to g mm is equal to k square, as r is equal to 1 over u from the trigonometric relation we previously studied. Then the law of force will be F into 1 over u is equal to minus k u square. The equation of central motion in terms of u is known as d square u over d theta square plus u is equal to minus m over l square u square into f of 1 over u. D square u over d theta square plus u is equal to minus m over l square u square minus k u square, cancelling the u square with u square. D square u over d theta square plus u is equal to mk over l square. That will become d square u over d theta square plus u minus mk over l square is equal to 0, giving that equation 2. Here mk over l square is constant. The second differential equation of the above equation will be u is equal to a cos theta plus b sin theta plus mk over l square. U is equal to a cos theta plus b sin theta plus mk over l square. Here a is equal to c cos phi, b is equal to c sin phi. C and phi are constants. We are going to work further. Hopefully till here you have understood. If there is any difficulty, you can discuss with me. Thank you.